Okay, so now let's use this update operation, also the theorem we just talked about, to see how to compute the shortest path distance. This is so-called the Bellman-Ford algorithm. Okay, in particular, the theorem we just described actually implies that if right now I already computed the shortest path distance estimate to all the nodes whose shortest path has only k edges, correct? Okay, so the distance may not be k, it's just the shortest path has k edges. Okay, then, so suppose those are all already correct. You can also, you probably also compute the estimate to many other nodes, but those we don't have a guarantee. Okay, but suppose for all the nodes whose shortest path is k edges away from the source already have their estimate correct. Okay, now what we can do is that we can perform updates to all edges. Okay, and after that, we must, if you have a node V whose shortest path has k+1 edges, after the update, this node must have its estimate correct as well. Why? Because if the shortest path from S to V has k+1 edges, that means that it must have to first go through some nodes where the shortest path has k edges plus the last edge from that node X to V. Okay, and by doing update on this edge, then we would get the because that estimate by our assumption is already correct. The estimate to X is already correct. By perform update by the theorem we saw just now, afterwards the estimate to V must be correct as well. Okay, so that's the idea. Okay, now in general, we don't know what edges would be relevant. To make sure that I'm going to perform update on this edge, I'm just going to update all edges once. Okay, which means that sometimes we perform updates on edges which is not needed. But as I mentioned earlier, the observation is that if you already get an estimate to a node correct, okay, then perform any extra update doesn't do any harm. It may not be needed, but it will not change this estimate anymore. Okay, once we found the shortest path, we cannot change it anymore. Okay, the update operation will not change it. All right, so let's see more detail. What does it mean? So let's look at this example. Assume that we're computing the shortest path from the source node S. Okay, at the beginning, we don't know anything, so we set all the nodes, the estimate to be infinity other than the source, which have 0. Okay, all right. So now what does that mean? So let me just mark it here. So at the beginning, this estimate is 0, but for everything else, I only have infinity. Okay, now another way to look at this is that S to the south, the shortest path has only 0 edge, and that's correct. Okay, now what I'm going to do is that I'm going to perform update on all edges. Okay, the order doesn't really matter, but let's assume that in this case, I first perform update on this edge as A, and then that find a better way to reach A, and we change when we do update, we change the distance to be 2, and then when we also consider S to be this edge to be the predecessor. Okay, and when we perform update on edge as B, we found a better way to reach B with distance 10, and this is a predecessor. And then when we do the same for C, we find a better way to reach C. What I write the number here are the estimate of a distance, okay? And the red edges are the predecessor of the best estimated path we found so far, okay? So we perform update on all edges. We can also do the update on edge AD. In fact, when I do the update earlier, let's assume that the order is that I first do the update on edge AD, edge DB, and BC before I do the update on SA, SB, SC. The order doesn't matter. I'm doing the specific order just to make this more interesting, okay? So when I do the update, so let's actually restart just to make this more clear. Let's say that we have the current estimate is the distance here is 0, infinity, 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 infinity. Okay, now I'm going to do update on all edges. Okay, so when I do update on edge AD, I didn't find any better way to reach D. It's still infinity. So I do nothing. Okay, same for DB, same for BC. Okay, then I do update on SA, and now we found a better way to reach A, which is 2. And this is a predecessor of this better estimated shortest path. Okay, we make it red. And the same when I update SB, the edge, I found a better way to reach B, and my predecessor of this new discovered shortest path is the S. Okay, same for C. When I do update on SC, I found a better way to reach C, and the predecessor along this path is S. Okay, so this is the first round. Now note what we observe is that after the first round, I got some estimates on A, B, C, but not all of them are correct. However, the estimate to A now is correct. Why? Because the shortest path from S to A has only one edge. Okay, by the theorem, since that before I run this update, the shortest path to S is already correct. So when I do update on this edge, then the shortest path from S to A is also correct. So after this, we actually already got the shortest path estimate to A correct. The shortest path to other nodes, B, C, or D, may or may not be correct. We don't know. Okay. Okay. Then they may be correct or may not be. Okay. All right. Now, so this is after the first round. Okay. Now, let's repeat. Let's say that let me do it again. Okay. I'm going to do I already got all those estimates, the shortest path distance from S to those nodes where the shortest path has only one edge correct. Okay, so let me repeat this procedure. Let's do the update again. So again, we use the same order. We first check the edge AD. Now when I do update on AD, I found a better way to reach D. I found that I could reach D through A. And I changed the predecessor of D to be A and the distance to be 3 now. Okay, now next I do DB. Note interestingly, when I do a DB, I found a better way to reach B, which is 3 plus 1, which is better than my 10 before. That means that now this is my predecessor. I found a new way to reach B, and this one is not anymore. Okay, all right. Now we do shortest path. Well, now I do an update on edge BC. Again, when I update on BC, I found a new way to go from B to C, which is the distance is 4 plus minus 6 is minus 2. Okay, that means that I found a new path to reach C, and the previous one is not the shortest anymore. So I changed the predecessor. Okay, then I continue to perform update on edge SA, but this doesn't find any new path for me. And then SB also doesn't find any new path, new distance, new path for me. And SC doesn't discover any new path. Okay. Now note that after now I perform a second round of update operation. Okay. What I can say for sure is that the shortest path to D must be correct. Why? Because the shortest path from S to D has 2 edges, okay? And it goes from A to D. Since A is already correct, when we perform update on AD, I got the D correct, okay? Now, I cannot say about the shortest path distance to the estimate to other nodes yet, but I know that to D, which is 2 hop away, whose shortest path is 2 edges, must be correct. Okay, in this case, it turned out that the shortest path distance to B and C are also correct, but at this point, I don't know yet for sure. Okay, so I continue, I perform this, and so this is after the second time. So those shortest paths, those nodes whose shortest path from S has at most 2 edges after 2 rounds of update would be correct. So both A and B would be correct. Okay, and then I continue to perform this, and every time I basically more and more those longer and longer shortest paths become discovered and become correct. Okay, in the end, it turned out that what I computed now here is already the shortest path. Okay, but in general, you keep repeat. Okay, every time you guarantee. So suppose after k such rounds of updates, you can guarantee that the This is the guarantee. After k times, you guarantee that all the nodes whose shortest path from the source has at most k edges are guaranteed to be estimated already correctly. Now, by running, performing updates on all edges one more time, one more round, then you basically reach all those nodes whose shortest path has k plus 1 edges are also guaranteed to be correct. Okay, and you do this till that we are guaranteed to find reach all the nodes, find shortest path to all of them. Okay, so okay, now how many times do I have to perform this update all edges operation in order to guarantee we find shortest path to all nodes? Well, here's where we need our observation. Remember, shortest path has to be simple. Simple means that the no nodes in the shortest path can repeat. Okay, as such, a shortest path cannot have more than v minus 1 edges, because I mean a shortest path in the worst case it will visit all the nodes. So there are v nodes along this path. The length is v minus 1. There's v minus 1 edges. Okay, you cannot have longer shortest path, because if you use longer, more than v nodes, then some nodes will be visit more than once. So it's not simple anymore. Okay, so in other words, the longest possible shortest path, longest in terms of number of edges, is at most v minus 1. Okay, that means that I only need to run my algorithm, perform this iterative approach, v minus 1 rounds. After v minus 1 rounds, then we can guarantee the shortest path to all nodes in V are estimated correctly. Okay, so that's, and this is exactly the Bellman-Ford algorithm that I just described. And here is the pseudocode, it's the algorithm in Python. It's rather simple. What are we doing? So we basically, this is basically the iteration. We basically run this v minus 1 times. Every time, very simple. We simply go through all the edges in the graph and perform update. That's it. So this is our so-called, in my description earlier, this is my update all edges. Okay, each round you just perform update for all the edges. Okay, and then you do this v minus 1 round, because after every round you guarantee that all the nodes, which is after k rounds, you guarantee that all the nodes which are whose shortest path has k hops, k edges from the source already discovered correct. Their shortest path estimates are already correct. Okay, that's it. And after v minus 1, since the longest, the shortest path cannot have more than v minus 1 edges, after v minus 1 edges, all the nodes has their estimate correct. Okay, so the time complexity, well, the setup time for this is just you have to set up 3 arrays in general, but using Python, we use a dictionary. Okay, so this takes order of v time, and each of the updates takes constant times. But how many updates do we have? Well, within each for loop, we need e number of updates, because you are going through all edges. You update all edges. And we have v minus 1 run. So altogether, the number of updates is v minus 1 times e, which is ve. Okay, the total time complexity as such is v plus ve, which is dominated by this. That's the time that we have. Okay, all right, so this is, I'm just putting it here again. It's the same thing. All right. Okay, so I will not go through this example, and you can, since I have another topic to cover, but you can go through this example yourself, performing Bellman-Ford on this graph, assuming this is the order of the edges that you're going to perform update on. Again, the correctness of the algorithm, the order doesn't matter. Okay.